Hey all, this is going to be the final video for the measurement error series. I just want to walk us through what I think the key conclusions are, things that you'll want to be familiar with when you're thinking about measurement error in your own work. First of all, we've got classical measurement error in X, which causes bias, downward bias, or bias towards zero in the coefficient of interest. I just want to make a couple comments on that besides the derivation that you already watched. One is, keep in mind that that derivation gave us some information, and that is that the bias is larger the larger the measurement error. And you can go look at the equation to see that, to see what makes the bias larger. So the more error there is, the larger the bias. Notice that the coefficients on other variables, if you're doing this in a multivariate context, can also be biased. They're biased in an unknown direction. So it's just the one that's measured with error that you do know it's understating. I like to remember that just by thinking about what would be the case if X was almost all error and barely any information, or mostly noise and very little signal. The idea is the more of that variable is just garbage, no information, the smaller the coefficient is going to be. It's not going to detect a relationship between that X variable and the Y. And so in the extreme case, if your variable is almost all measurement error and not really any information, your coefficient should be around zero. Again, because we're assuming that the error is mean zero, that the error is uncorrelated with Y on its own. The only correlation you're going to pick up between the mismeasured X and Y is going to be from the actual X that's buried in it. And so the more error there is, the closer that coefficient gets to zero. Note that if more than one variable on the right-hand side has measurement error, you really can't make any more assumptions, or you can't draw any conclusions about the direction of bias, even for each of those two individually, because they can each be affected by the measurement error of the other one. So, bad news. Second measurement error in Y, we saw that's a lot easier to handle. It results in an unbiased coefficient. The main issue is a loss of efficiency, big standard errors. If you have measurement error in X and Y at the same time, it's just what you'd expect. You're going to have bias downward for the coefficient, and you're going to have big standard errors. The third piece that I wanted to mention here is the reverse regression strategy that Hausman mentions for bounding the bias. And this is just a strategy where you actually regress X on Y instead of Y on X. And Hausman walks through how doing that actually gives you another biased estimate of the relationship between Y and X, but in such a way that it will create an upper bound for the true value of alpha. And that's really helpful because the alpha that we have in the context of measurement error is not large enough. And so we know that it's an underestimate. So the reverse regression can give us an overestimate, effectively giving us bounds on what the true alpha might be. Two other things I want to note from Hausman. Hausman talks about IV as a potential solution to measurement error on the right. So I put a little 1 here to say that it's classical in X. That's when we're thinking about this IV strategy. You can think about the mismeasured X the same way you think about any endogenous variable, because there's a piece of it hiding in the error term. They note that you can use instrumental variables, but you should be careful. Weak instruments can get very ugly here. And so anytime you're using an IV, you've got to watch out for that. Hahn and Hausman present a specific test that's mentioned, that after you estimate the model with two-stage least squares, you can do a reverse regression in two-stage least squares. And essentially what you're looking for in that case is that the results should be pretty similar to each other, because if the IV is solving the endogeneity problem, then the upper bound and the lower bound should be very close, meaning they've really zeroed in on the estimate. And so that's something to try. The last thing I want to note from the article is in the case when we've got we've got measurement error in Y. So thinking about the Y side, but number 5 is, what if Y isn't continuous? What if Y is binary? If Y is binary, it literally can't have classical measurement error. That's really important. Classical measurement error looks like mean zero with basically a normal distribution around it. And when you have a binary dependent variable, the nature of the measurement error is misclassification. You either get it right or you get it wrong for each person. Each person's measurement error is either 0 if it's not measured with error, -1, or +1. Those are the only possible amounts of measurement error in a scenario with a binary dependent variable. And so you want to note that in that case, you really do have a more serious problem. You can't simply say you've got some inefficiency, big standard errors. If you've got misclassification, the results are going to be biased and inconsistent. And so Hausman and others provide suggestions using things like maximum likelihood estimators or nonlinear least squares. And you can dig into that more if that's something that you need for your work. Notice also, even if the left-hand side is continuous and mismeasured, one of the strategies we've talked about recently won't work nearly as well, and that is quantile regression. Quantile regression depends upon you having roughly the ordering right. If something's mismeasured, there's a good chance that your ranking of the order of the values is not very good, not very reliable. In that case, OLS is actually a better option because, as we proved, OLS is unbiased. That's because, again, we've assumed the measurement error is mean 0, and so our measurement error assumptions are around the conditional mean, whereas median regression relies on assumptions about the conditional median, which we're not making when we set up a classical measurement error model. So if you're thinking about using quantile regression in the context of measurement error rather than something like censoring, you just want to think carefully about whether the nature of the error justifies using a quantile strategy. That's everything I'm going to say about measurement error. What we'll be doing when we get together is I'll be taking questions or comments, any thoughts that you might have about the measurement error stuff specifically, and then we're going to mostly discuss the Kim paper, which has a misclassification error problem that I think you'll find interesting. He walks through it in the context of the question he's asking, but also walks through some of the technical details about the nature of the measurement error. So I think you'll learn a lot from the paper. I'll look forward to talking to you about it soon. Bye.